for recording. Okay, so now I have started to record. As I said, I can't open the other camera because I'm not sure what happened again. We just want to continue our job. But if you have any question, again, when I maximize the page, I don't hear you. Okay, sorry, I don't see your chat. So somehow somebody need to remind me something is in the chat, or if you can just really unmute yourself, that would be really helpful. Okay. As I said, the plan for today is just two sections of, both of them are linear differential equation. One of them is just how we solve linear differential equation. The other one is one application of first order linear differential equation. Okay, so this is just a different type of differential equation. How do we call some differential equation to be linear? So first of all, is first order, because we will learn more like second order differential equation or more in the next chapter, but these are all first order, so means it's just really the highest derivative that you see in differential equation is first derivative. And then it's called linear. As you see, you have really the highest is the derivative with respect to the x, and then you have the zero derivative, which is just the y itself, and then everything else has no y, so you shouldn't have any power to the y. You should not have any anything like just sine or cosine, anything for your y, but it's fine your x's to be just really any function, like just here is one function in terms of x, one function in terms of x. It can be any of the functions like sine, cosine, tangent, and nonlinear, linear. Okay, but what we call it linear means the y itself should not have any power or any to be in argument of any of the functions. Okay, so one thing that we prefer to make it better, we just say let's say always this leading coefficient equals 1. So if you want to make the leading coefficient equals 1, you have to divide the entire equation by a1. So then you have a1 of x, then you have dy dx, and then you have a naught of x, and then you have y, and then you have b of x. So you divide by a1 of x, you divide by a1 of x, and then you divide by a1 of x. So that is dy dx, and this is a naught of x divided by a1 of x. This is y, and then you have bx divided by a1 of x. Okay, so that's just really the other way or the better way of writing the linear differential equation, because in this case the whole thing is called the function of the p, and then this whole thing is called just the function of the q right over here. So this is the form that we prefer always to see, because that's the way that we know how to solve it. Okay, so the goal is always to make this this number right over here to be 1, and then have a derivative by itself, so y prime or dy divided by dx. Then you will have a function of x, then you have just the y by itself, and then your right side has no y, so it has to be all in terms of x. So your right side has no y or y prime anymore, it's all in terms of x. So that's how we standardize the equation before solving. Okay, the way that we solve it, I have a little bit of the proof, and then we will learn why this proof looks like this, and then it gives you actually a method of solving, or the factor that you need to multiply to solve. Okay, so what it says if this is just really in this form, so I can just add one example. What do I mean by this form? So I just have some example, like just y prime plus 2x, y equals 2x cubed. So that's just one example of the linear differential equation, which in this case, this is going to be your p of x, and this is going to be your q of x. Okay, so that's just the linear differential equation, first order linear differential equation. Okay, so again, this little proof is just trying to tell us why we do need to multiply by a factor to be able to solve it. Okay, so the method is going to be again integration. I want to integrate later, but I think I forgot to press recording. Am I right?
Yeah, it has been recording.
It's not recording, right?
There was a thing.
Okay. Yeah, just making sure. Thank you. So then what I do is, I find by now, what I do is just really find something which later has a name. We call it integrating factor, which we call it mu here, but it has different name in different books. It doesn't matter what you call it. It's really what the factor we need to multiply to able to solve this type of differential equation. Okay. As you see, it's multiplied this extra factor of mu, which again later is called the integrating factor. So then the goal is to make the left side to be derivative of some function. So the left side must be the derivative of is somebody must be on mute. Okay, the left side is just the derivative of a function, actually product of the function, product of two functions. Okay, so then if I just want to practice, I mean, if you have f times g prime, it has to be derivative of first one to the second plus derivative of second one to the first. Okay, so if that's happening, seems I have to have, if I just go by right order, so it's just have something multiplied by dy dx. So that's just really says this piece. Okay, so then you have derivative of first to the second, and then this has to be really derivative of something, right? So if that is going to be, so let's just say in this way, I have called my f to be y, and then my g to be just something, huh? I don't know, what do I call it, mu of x. Okay, so so then this side is derivative of y and times the g of x, and then this side has to be derivative of g times y. This one has to be derivative of g times y. So this has to be the derivative of the g. This has to be derivative of the g. Okay, so this is just telling me whatever is the mu prime must be mu x times of p of x. Okay, so does it make sense? If the left side is the derivative of product of two functions, which one of them is y, the other one is just mu of x, so that whole factor, which I made it by the pink color, has to be the derivative of the function. Then I'm right. Okay, so that's just really a differential equation, which easily I can solve it, because this is just mu prime of x divided by mu of x. This is true if the following is true. So which is just the process of solving this, and is going to integrate both sides, and that is natural log of denominator, and this is the p of x. So then I need to e both sides, and then that gives me mu of x has to be e, oops, I left my integration notation. That would be e to the integration of p of x d of x. Okay, and that's exactly what we call it integrating factor. Integrating factor. Okay, so from the beginning I didn't know what's a mu, and then by the assumption the left side is going to be product of the two, sorry, the derivative of the product of two function, then I just actually formulated the mu to be in this form, and that's just really what we need for the steps of that. So if this is just going to be, the left side is going to be the derivative, so I'm just going to rewrite my left side. Let me just make it in blue. So this is going to be mu of x then it was dy divided by dx, and then I have had what we call mu prime of x, and then times the y, and then this side it was mu of x times q of x. Okay, and this was just mu x times y derivative, product of two functions on left side. This is mu x and then q of x, and then integrating both sides, so that gives you integration by derivative cancel out, mu of x times y equals integration of mu of x times qx dx. So then the solution is going to be 1 over mu of x integration of mu of x qx dx, and actually for sure it has the what is it, constant of integration. So then this is just what we call the solution to that differential equation. Okay, so this is the way that we solve that differential equation. To wrap what's happening over here, that's just really these steps. Step number 1, you have to make it in this standard form, which is very important. You have only 1 over here. You have to have a function of x, and on right side there shouldn't be any y or y prime, so everything has to be in terms of x. So this is the standard form of the linear differential, first order linear differential equation. So the next step is the extra factor of the mu, which is just e to the integration of px dx. So that's just how I proved y is in this form. So I just showed you that's just the steps. Y is that integrating factor in that form, and then it says multiply both sides of the equation with that mu, and then write the left side always as a product of the two function, and then start to integrate. Okay, so the way that I have done this proof is really the way that we need to solve the first order linear differential equation. First we standardize it, and then we just say what is the integration factor, and then we multiply both sides and we make it as a product, and then when we have them as a product, we integrate both sides and solve it for y. Okay, any question or any concern, anything that you want to write down over here? Should I give you time to write down? No? Again, when it's maximized, I don't see your comment. So no, right? So we are fine. Then I have my first example to try. Yeah, because the page is too big. So this is my first example to try. What it is, it's already in a standard form. It's already in a standard form. And then it seems there is a typo. Then I need to make sure I add the y over here. Otherwise, it's not in a standard form. Let me just rewrite my standard form one more time. So it has to be y prime. Then it has to be a function in terms of the x. Then it has to have the y. And then it has to have the other side, a function in terms of the x. Okay, so this is the standard form. So what I need is step number 1, it should be in a standard form, which is already standard. And then that p of x is 2x plus 1 divided by x, q of x is just e to the negative 2x. And then step number 2 is what's that extra factor that I need to multiply to be able to integrate, right? So find integrating factor, and then however you want to call it I or mu, it doesn't matter. So formula is integration of always px dx. So e to the integration of your px was 2x plus 1 divided by x, and that's dx. So then again, it's just really e to the If I separate it, it's just 2x divided by x plus 1 divided by x dx. I have to say integration of x, which is, sorry, 2 plus 1 over x dx. And then this is going to be 2x plus natural log of the x. Is that fine? So mu of x is e to the 2x e to the natural log of the x. Okay, then it is, because we could separate it by the properties of the what we call what is it, product rule, huh? So that is x left, so this is just x left e to the 2x. So that's just your integration factor. And it's really important to know, first of all, that piece does not have the constant of integration. Okay, no constant of integration, and I will explain at the end why we don't need the constant of integration in this step, because we take care of one constant at the end. And then that the other thing is important to just write it in the most simplified form. So if you know any properties of the e, if you know any properties of the natural log, you must use it in algebraic way and simplify it in very nice form, because otherwise the integration will be really tough. Okay, so you have to have the most simplified form of your mu to able to continue. Make sense by now? So that's my integrating factor. So then step number 3 is multiply both sides. Do I have any question, guys? Is there any question? No. Multiply both sides of differential equation by mu. Okay. So then I will rewrite my dy by dx was there. I have plus 2x plus x then y. And then I have had e to the negative 2x. So this is multiplying by x e to the 2x, multiplying by x e to the 2x, multiplying by x e to the 2x. So then this is just my integrating factor. So then the left side you need to remember is always, always, always derivative of product rule, right? So derivative of the product rule, so one function is always y, the other function is always your mu. Okay, so you can test one more time whether that is true. So if I go by product rule, I have to, let me put my charger. We don't want to get disconnected again. Sorry. So you can check one more time. So let me just make it lighter. So this is the derivative of y right here, and then this is as it is, and then derivative of this thing, derivative of this thing is going to be itself multiplied by derivative of this. So you can just do it one more time because it's just a product rule, so that to make sure that is true or not. Okay, so what the claim is, derivative of x e to the 2x is 2x plus 1 divided by x times x e to the 2x. So that's just really making 2x plus 1 e to the 2x, and that's true. This is really true because it's the derivative of product of two function, and that's as I said is derivative of x, which is 1 times e to the 2x, and derivative of this one is 2 e to the 2x times x. So this is really what it is. Should I worry about that? Not really, because if you have done this step correctly, if you have done this step correctly, it's just always here mu of x times y and then derivative of the entire thing. Okay, but you can always test it to make sure your computation in previous step was correct. Okay, if not, there was something wrong with the computation. Otherwise, that should be the proof. The theorem says that should be always true. Left side has to be the derivative of two the product derivative of these two functions, okay? So then here I have x left because e to the 0 is going to be 1. So that's x left, and that's it. This is just really nice to integrate. So this is really nice to integrate. This is integration both sides because derivative and integration are opposite operation. They cancel out. And derivative of x is x squared divided by 2 plus constant of integration. Okay, so that's just the place I need my constant of integration. Since the equation solve for y, or your unknown function is called y, so you keep the y this side, and then you divide both sides by the x e to the 2x. Okay, so you can leave it like that. If you like, you can distribute it. I usually don't distribute, and it's fine. But if you want, you can just really distribute this one and just continue. But that's just really perfect. That's your answer.
Professor, I'm kind of confused on the second term and how, or in step 3, how you go from like those two terms to that that product right there with the derivative.
Mm-hmm.
I wish I could point to it, but um, yeah, it's like, how do you go from that to that again to the product below?
So why is in that way? I need to go back to the previous slide. So remember, to prove this formula, we consider we assume the left side of the left side of this is derivative of the product of two functions. Okay.
Okay.
So y is in this form. That's why, because that's how we got our mu. That's how we define what the mu is. How we evaluate the mu to be like that. It was just based on that fact. Okay.
Okay.
So then for every single equation, when I'm writing the left side, it's just really the product rule, because it's the derivative of the first, which is derivative of the y in terms of x times the mu, and derivative of the mu times the y is just right over here. So it's just two terms. And then this for specific examples, I can go back there and see it's always true. If you get the previous steps correctly, that should be always true. Okay. So
Okay.
the rule says the left side is just the product of two functions. So the left side is just product of the two function derivative. Okay. So then derivative of first, so I'm testing whether I'm right or not. So derivative of y is sitting right over here. So this is derivative of y multiplied by the same as the x e to the 2x. And the claim is, if everything is correct, if I'm just right in my computation, the claim is this is going to be, this whole thing is going to be the derivative of x e to the 2x times y.
Someone said they can't hear on chat.
It's Brandon. Brandon says he can't hear anything.
Why, Brandon? Brandon, are you okay?
Yeah, I can hear everything now.
Okay. So let's just move back. So then what I was trying to say, the claim is whatever is in green now is the derivative of x e to the 2x. And I was testing right over here whether that claim is correct or not, right? So I was the claim is the derivative of x to the 2x is going to be that thing, right? So derivative of x to the 2x is supposed to be, based on what the claim says, 2x plus 1 divided by x times x e to the 2x. And then when I know, I mean, I simplify by just the product rule is really true, right? So the derivative of x is 1 e to the 2x, and the derivative of e to the 2x is 2 e to the 2x times x. So that's true, okay? So the only reason that I'm testing to make sure my previous step, that was the simplification, is correct. But that's always based on the way that we found the formula. Left side is derivative of the product of always mu times y. I'm fine, Joel, to continue.
Yeah, that makes sense. Thank you.
Any other comment, question? Okay, so let's practice one more example. If you don't have any question, let's just practice one more. Sometimes people just say we have a formula setting that is just the one that I boxed it on this page. So let's just go back to that page. This is the formula. They just say, okay, I memorize this formula always, and then I just say step number 3 is just really go by this formula. I don't like that method, but that just really I mean, this course has enough formula to memorize, so please show me the steps. Oh, I have skipped one example. Sorry. It was just really not showing me this one. Okay, so let's now try this one. Okay. So we tried example number 2. Now let's try this one, then IVP. Okay. So step number 1, it has to be standard form. So standard form. So this, just to remind you, is going to be one derivative, and then you have p of x, and then you have y, and then you have to have a q of x at the other side. Okay. So this is not obviously standard. What do I need to do? Multiply by x to make it standard, because that 1 over x should not be there. So that makes it dy by dx. That makes it 2. 1x cancel out, 1x left, and then that is x squared cosine of x. So this is just to standardize it, right? So then you just have to say p of x is negative 2 divided by x, q of x is just x squared cosine of x. Fine? Is that okay? Then I have step number 2, so which is find the mu, right? So find the mu, which we call it integrating factor. And that has a formula. So then mu, or integrating factor, e to the integration of px dx, which is e to the integration of negative 2 divided by x dx. So that is e to the negative 2 natural log of x. And then this is e to the natural log of x to the negative 2. So that gives you x to the negative 2, or 1 over x squared. As I said, that's the most important part. I need to have the most simplified form for the mu, right? And that is going to be step number 3. So that's the factor that I need to multiply, right? So multiply both sides by that mu of x that you have had 1 over x squared. Okay. And this is going to be 1x squared. Then I have dy divided by dx. Then I have minus 2x, and then integrating factor, and then y, and then x squared cosine of x, and then integrating factor. Okay. So this is just correct. Okay. So then I have to know one more time, the left side is always product of the two functions and then differentiate. So the right side is easy. Let's just say x squared by x squared cancel out. So just cosine of x left. So the left side, as I said, it has to be 1 over x squared and then times y, then derivative of that. Okay. So this term, again, if I make it in the green, so this thing claim is derivative of this thing. And just to make sure my computation is correct, so 1 over x squared differentiate is going to be minus 2x squared times, sorry, that was just x. x squared. Okay, and that is true, right? That's minus 2 divided by x cubed, and that's just really derivative of 1 over x squared. Yes. Okay.
So even though there's a 2, we can just say the derivative is equal to that?
What's the derivative of x to the negative 2?
Oh, okay. Sorry.
Yeah.
Yeah, sorry.
That's
It's been a while
that's
since I've done derivatives.
that's fine. Okay. So then everything is fine. I have to start to integrate both sides, which gives me integration by the derivative cancel out, their opposite operation. Cosine is sine of x, and then plus c, right? Plus constant of integration, and that's it, you got it. So you multiply both sides by x squared, and then you write it like this, and that's your answer. Is there any question? Is there any question for me? No, move on. We have nothing in chat, so that was my second, sorry, actually first example. I've done my second example wrongly first. So this is here. This is here. So that's just IVP. The last one is IVP. The only difference is I have to take care of my constant, right? Otherwise, IVP is just really another differential equation. Okay. Is it the standard? Okay, so I have to have derivative by itself. I have to have derivative by itself. I have to have a function of x. I have to have y, and then I have to have everything only in terms of x on right side. Again, it seems the only problem is just this factor. You must divide by x squared plus 1. You must divide by x squared plus 1. Okay, because that has to be always leading coefficient equals 1. So that gives you 4x divided by x squared plus 1, then y, and then you have x divided by x squared plus 1. Okay, so p of x is 4x divided by x squared plus 1. Q of x is x divided by x squared plus 1. Is that okay? Is there any question? Is there any question? Okay, so then find the mu. Find the mu of x, which is always integration of p of x dx, or what we call integrating factor. Okay, so then that should be a little bit nicer integration probably. No, it's just really natural like, right? If I take u is x squared plus 1, du is 2x dx, so that is 2 du divided by u. So this is e to the 2 natural log of u, which is x squared plus 1. So again, I have to take care of all the properties of natural log and e. to simplify this one. So this goes by this, so that gives me x squared plus 1 to the second. That was the property jumped here. So if you don't remember, natural log of x to the power is power natural log of x. That's the rule. Is that okay? Then this step number 3 is going to be multiply this factor. If your mu looks just really ugly, complicated, somehow hard to integrate, you have done a mistake somewhere, you're missing negative, you're missing some power. So otherwise, if it is the first order differential equation, it has to be after multiplication, nice integration, okay? It's not really a complicated integration, it just has to be first calculus level of integration, not the second calculus, okay? Unless you have done a mistake, otherwise it should be fine. Multiply both sides by mu, which is x squared plus 1 to the second. So then I have x squared plus 1 to the second dy dx x squared plus 1 to the second 4x x squared plus 1 y, then x squared plus 1 to the second, and then x squared plus 1. So ready? Claim is the left side is the derivative of always mu x times the y. So mu x is x squared plus 1 to the second, and then y is y, right? So that should be true, right? It should be true because this is left to be the, sorry, didn't change it. This is left to be the whole thing to be the derivative of this. I'm not going to test it one more time. It is true, okay? So this by this cancel out. On left side, next step is integration. On left side, I have x times x squared plus 1, x times x squared plus 1. And the next step is integrate of this derivative, and then integrate of this nice, let's just distribute x cubed plus x, and then dx. Integration derivative cancel out, and that is going to be x to the fourth divided by 4, x to the second divided by 2 plus constant of integration, and then this is it. So you divide both sides by your mu thing that should not be on left side, then that is your answer. If you want, you can distribute, but I don't suggest you really leave it like that. That's fine. Does that make sense? Any question? Is there any question?
Professor,
Mm-hmm.
this is a IVP problem, right?
Oops. Yep. Thank you. So I left my value, which was y at 0 equals 10. So then x equals 0, then y equals 10. So then I can take care of my, so that's what we call general solution. And now I can take care of my constant, right? So x was 0, y was 10. One more time, let's just check it. X was 0, 1, 10. So 10 equals 1 divided by 0 plus 1, and then 0, 0 plus c. So then c is 10. Yeah, that's just easy. Thank you. It was close to forget about that initial condition. Okay. This is now what we call particular solution to IVP. Make sense? Any question? No? Okay, so I think I have one more example. Oh no, I have two more examples. Okay, can you please just give you a minute to try to make it in standard form? Okay, so I have to make it in this form. Okay, just right now, make it in a standard form. And give me what is your P of X and Q of X. Do you mind if we don't have camera on? Because I scared to make it on and then we get exactly same problem again. Should I test it? Or it's fine without the camera?
Yeah, we don't need the camera.
Okay. Okay. So, ready? That was step number 1. Standard form. Okay. So then I have had y prime. I have had sine of x, secant of x times y. And then I have had 2 sine of x. Okay. Can I simplify sine of x times secant of x to the tangent or no? Is that true? Right. So that gives me y prime minus tangent of the x, y equals negative 2 sine of x. Okay. So yes, this is P of x, and this is Q of x, and then I just need to integrate, huh? So step number 2, find mu of x, which is e to the integration of P of x dx. So then I have mu of x, and what is integration of the tangent? And what is the integration of the tangent? Is okay. I got minus natural log of cosine of x, but I think some of you memorize, I remember from last class, is natural log of the secant. That makes sense, right? Because that's really the same as natural log of cosine of x, and that is to the -1. And that gives you natural log of the secant. It's the same thing, okay? So however you like it. So either one, if I write it minus out, then I have minus natural log of cosine, and the negative one negative cancel out, is just really cosine left. It's just really cosine left. Is that fine? Agree with me? So that's what I was looking for, to multiply both sides. So I will write my original problem looks like this. And then I have to multiply by cosine of x, then cosine of x, which is my integrating factor. So the claim, which is always true, is the left side has to be derivative of the product of the y and the mu. Y and the mu. I just write it the other way. Cosine of x, the y. Okay. So derivative of first one, y. Derivative of first one, which is y prime, times second one, which is the cosine. Derivative of second one, and actually this is simplified, right? So let's just write over here this to simplify to just sine of x, right? Is that true? So that's simplified to sine of x. So then you just have to say derivative of cosine, which is negative sine, times the y, and then you are right, okay? And again, you don't have to test it. This is just really to make sure the previous step was correct. And then I start to integrate. That is just same thing. Integration and derivative always cancel out, so they are the same thing, -2. This several ways we can do this one. So we can just use u substitution, u to be sine, and then du is the cosine. You can just say, I want to say u is cosine, and then du is just negative sine. That's fine. You might say, okay, now I've learned in what is it in trig, 2 sine of x times cosine of x is sine of 2 times of x. So this whole thing is sine of 2 times of x. However you do, that doesn't matter, okay? So you'll get the same answer. It's not really same answer, it's just really after trig simplification, you will get the same answer, okay? So then up to you. You can use either of these u substitution, or just use the trig and then say this is going to be minus sine is cosine divided by constant plus constant of integration. Integration of sine is negative, so it's plus. Then you get the y. That's it. If I was just really doing any of the other green or what is red substitution, then it was just maybe somehow getting simplified in this step. easier, but now I'm fine with that. Okay, so you just leave it like this. Okay. Any question? Is there any question? Next question says, is this differential equation linear? If yes, find the general solution. Again, I think it's just, yeah, it's a break time. Okay, so let's just make a little bit break, and then at the same time, if you have, I think this is the last example for this class, I mean for this section, and let's just say 7 minutes break first, and then try this problem by your own. Okay, I came back to the chat. Yeah. Okay. Seven-minute break. So 12, huh? We'll come back at 12. I mean, I'm here, but just start at 12. Okay. Is this one, let me check whether I have anything in the chat. No. Okay. Is this one a linear differential equation? What do you think? Linear can't have second power, right? So that can't be linear. But we won't know unless we really standardize it. Okay, so if it's supposed to be standardized it, so it has to be dy dx, and then it has to be a function, and then it has to be a y, and then it has to be a q of x. Okay, so seems one way is just make this one to be dy dx, right? So that gives you y squared, and that gives you 3xy minus 1 dy dx equals 0. Then I keep the dy dx, and then I multiply, and then I multiply, and then, oh no, sorry, I should divide by. So it was easier to keep it in that way. So it was easier to keep it in the dy dx, and then divide both sides by minus 3xy plus 1, divide both sides by minus 3xy plus 1. Is that fine? I've moved it, there was plus, I moved it to the other side, that makes this one negative, that makes this one plus. And then since this is now dy dx by itself, and this is going to be y squared divided by 3xy plus 1. Is there any hope to able to write by this format? Any idea? So remember, the only two types of differential equation you know how to solve, it has to be either separable differential equation or linear differential equation, and then otherwise I don't know how to solve it, right? So if it's a linear, it has to be that nice form or standard form. If it's separable, it has to be separate. Any idea about this? Okay, let's say, do we have, okay, so this was, it seems this one is, there's no way to separate somehow to write it in that way. So let's say if we have dy, then dx px y equals qx. Can I write this one is dx dy, this one is p of the y. In this case, mu is e to the integration of px dx. In this case, mu is integration of py dy. What do you think? Is there anything wrong to switch all x's to the y and all y's to the x? That's possible, right? I'm not sure whether that works for you, but that's just to remind you there are some problems in your homework. The y is a function of x. There are some function x is a function of y, and that's possible. That is possible, okay? But this is, I don't know, I'm going to test. If it does not work, so then I don't know how to get the general solution as of now, but I will find it, okay? We will find it later. So that was divide by dy, that was divide by dy. That gives you y square, sorry, I don't want to make it different color. So that gives you y square, and this is dx dy, and this is 3x y minus 1 equals 0 for now. And then if I look at to the pattern, sorry, that was dx dy. So I don't need to have the y square. I have to divide by y square. I have to divide by y square. I have to divide by y square. So that gives me dx dy. That gives me, I need a function of y, huh? So this is 3 divided by y, and then x by itself. And then the other side is 1 over y square. Looks good. Yeah. So you have the function x in terms of the y. So then you have something here, which is in terms of the y. And then you have something here, which is in terms of the y. So there seems it's a linear differential equation. It's the other way. Okay. So again, there are limited type of differential equation we know how to solve. So, and then the way that we check them is just really from the first one that we have learned. If it is separable, obviously we separate them. We don't worry about the integrating factor. We don't worry about the linear differential equation. First order linear differential equation. Here, if it was possible to do it in this way, obviously we do it. Okay, and there are two more types that we'll see after break. But since it wasn't possible to do in that way, so I had to just make it in terms of the x, or alternative way, which was in terms of the x, and then the function has to be as a function of y. So all I need to do, switch all x's to the y, all y's to the x, and that's fine. Okay. So p of the y is 3 over y, q of the y is 1 over y squared, and so on, right? So step number actually 2 is find the mu, and that is e to the integration of py dy. So mu of the y is e to the integration of 3y divided, that's just e to the 3 times of natural log of the y, and that's y cube. Then step number 3, multiply both sides by mu of the y, that is going to be y cube, and dx divided by dy, y cube 3 divided by y x, and then y cube 1 over y square. So this is from here, which I multiply every single thing by y cube. Okay. And then we know the left side is going to be the product of the mu y always times x, because now every single x is replaced by y. It was originally mu x times y, now is mu y times x. So mu y is y cube, and then x is just x. So this is my left, y left, okay? So then I start to integrate both sides. Dy, and that gives me y cube x left, that gives me y squared divided by 2 plus constant left. So x is 1 over y cube, y squared divided by 2 plus c. The problem is when we do one problem in one type, it doesn't mean it's only that type, because something could be separable at the same time linear too. Okay. So you might think that's a mistake, but it's not. So you might do something separable, and then it's just possible to be linear too. And then we will learn 2 more types. It's just really combination of them. Any question? That was a good one. That was a good one because it was different, right? So that was a good one because it is different. So that's what I have for this section. Is there any question about linear? So always there are 3 steps. First standardize it, then get the mu or integrating factor, multiply, and you get your left side to be the product of 2 function derivative. And then when you integrate, integration and derivative cancel out, so you have only the function. So what you are looking for is always this thing. So you can just solve for that. Is there any question? I'm going to move to the next section. According to the schedule, we have only one section of chapter 3. So we have only one section of the chapter 3. And that's just, chapter 3 is called compartmental analysis. Compartmental analysis. So what it is just really modeling your problem. It's application problem, and then it's just modeling your problem. Obviously for now, because we have learned only separate differential equation linear. So that's just really 2 types of the differential equation that you can model and you can solve it, right? So if you have any problem in real world and then you want to just solve it by using differential equation, the first step and the main step is always formulated. It's just really like any other word problem. You have to able to write corresponding differential equation first, and then you can just really develop, okay, that works for any type of the similar situation, and then you can just test your model that you made. Okay, so this is just for modeling any real world problems. One of very common, I will say traditional example, which is in this course, is mixture problem. Mixture problem or mixing problem is just one of the common or traditional example for first order differential equation, or is just the simplest way, I will say, to model a problem. Okay, So what it is, the base of this problem is you have a tank. Oops. I think we have room to just make it over here. So we have a tank, and then it is just something inside, liquid water. So whatever is inside, there is just by some rate, water is coming in, and then by some rate, the water is going out, okay? So what is the question here? Let's just read the question. So the basic one compartment system consists of the function of f of x, and that's just amount of substance. So you might have just salt, you might have just pollution, so you might have something in your liquid, and that is changing per time, okay? So if you have a substance which is changing in terms of the time, that is called the function of x as a function of t. So the some rate is input rate, which is just from through this pipe, which is coming in, and then the other one is just your output rate. So the other one is your output rate. So then whatever is right there is just something that is given in the problem, and we know it by real world that is given. So, and that is just really what's going on in the entire problem. To formulate it is just really remembering whenever you have the change in your substance inside that water or liquid, so the rate of change is the difference between these two rates. So whatever is going in and whatever is going out, if you subtract it, that's just the rate of change of the substance inside of that tank, okay? So always input rate minus output rate gives me the rate of change for that substance. So whatever is just really the solid or liquid is inside that tank, okay? So this just really notation wise, we don't have to use the same notation, so it's just always different from different application problems. So it just says the x, let's see, to be how much we have the salt or pollution, so whatever it is inside that water, per minute, per second, per hour. So it depends on what's the problem. And then the volume of tank is not necessarily the same. The volume is changing. It depends on what is the rate input and the rate output. So the volume in terms of the time is just V, not the speed. This is not the speed. This is the volume of this liquid or fluid inside the tank. And then C used for concentration. So again, the notations are not really unique for all entire this section. It depends on one to the other. So V is for the volume for now, C for concentration. At per minute, per second, per hour is just really depends on which unit time we are using. And then X is just how much salt or how much substance we have in the entire tank, okay? So what's the goal is to formulate this thing. So the rate of change for that substance is going to be input rate minus output rate. And that gives you a differential equation of first order. That gives you, that's supposed to give you the first differential equation, first order differential equation, okay? I don't think any of us have any problem about the concentration is going to be always the amount of whatever is substance per volume. So that's what we call concentration, right? Concentration is how much salt I have in entire 1 liter or 1 gallon water, right? So that's just the amount of mass divided by entire volume that we have. So per volume is going to be what we call concentration. And then this is just to get the equation, right? So if you want to see how the volume is changing, I just say volume in minus volume out. So the second volume is just after just having the more water or just really draining more water. So the original volume is V sub 1 minus whatever is just after changing is V sub 2. And then since it's changing per time, So that changes whatever is the rate is coming in, which is rate sub 1 is the flow in, and then rate sub 2 is flow out. So difference of the volume is whatever was originally V sub 1, whatever is after changing is V sub 2. So then the V sub 1, it depends on whatever is rate in, and whatever is rate in is called R sub 1, and then whatever is the rate out is called R sub 2. Okay, so this is giving me the difference of the rates in minus out times delta minute, delta second, delta time. Okay, so then if I want to just write the differential equation, the volume, so that means the volume is changing per minute, per time, by subtracting the rates. So the volume is changing per time by subtracting the rates of in minus rate out. So this is giving me the formula for finding the volume of this tank per unit time. Subtract the rates times time. If there is any initial water or liquid inside, so you have to add it, okay? So that is giving me the formula to find the volume per time. So whatever is rate in minus whatever is rate out, multiply by the time, and that's just y. So this is y is happening in this way, okay? Because it's really initial volume minus the second volume that I have. Is there any question for this process? Do I have any question here? So as we have had what do we call substance is concentration times the volume. So substance is just concentration times the volume, for because of how or what do we call concentration, amounts of the mass per volume is called concentration. So that's why X is just concentration times the volume. So how this how this substance is changing in entire water or liquid is just really the initial concentration times the volume, and then second concentration times the volume, okay? So it's just really what we have in minus what we have out. So that gives you the difference between this substance inside your liquid. And that is just replacing what do we call volume is rate times per minute or times the difference of the time. Volume is just rate times just how much or how many hours that drain is open or that pipe is open. So that's giving you how much the volume in, and then that's giving you how much the volume is out, multiplied by concentration, gives you what's the amount of substance. And then when I replace this, these are constants, so this is on my hand. I'm not worried about this thing. So this is already given. What is the rate in is given. What is the concentration was originally is given. But whatever changing is just really concentration out. So concentration out, because the water is coming in, the water is going out, is just not fixed. So your concentration is changing based on the volume, which is per minute or per hour or per unit time is changing, and times the amount that you have had, right? So this part, the concentration over here, which is the second concentration, is not fixed. This is changing, okay? And that's just really where the differential equation is coming. This is just the place the differential equation is coming, because that is really first order differential equation. So you have had this one originally was the function x as a function of t, or the amount of whatever you have inside your water as a function of t, and then you have had c1 r1, which is the initial minus the output, and that gives you really what you need for first order differential equation, right? So for first order differential equation, seems this is going to be your p of t, because the function is t per time, and this function is q of t, okay? So this is just the derivative, is a standard, what we call first order differential equation. This function right over here, which I made it in blue, is going to be my p of t, and then this function, whatever is on right side, is q of the t. And it looks better, or it's just more applicable based on given information if you want to replace this by the formula of the volume. Okay, but sometimes I prefer really to do this step in separate equation and get the result and plug in this denominator, then it's just really shorter. I don't know, how do I get rid of this thing? Is right on my equation. No way, something happened. Let's undo. Yeah. Okay, and so the whole story is just really to show by having the fact that always this green thing, the rate of substance per time is going to be input rate minus output rate, with just formulating all these notations based on the, I will say, really simple fact of the concentration, is giving you what we call first order differential equation corresponding by this problem. So we could formulate this to be our first order differential equation for this type of what we call mixing problems. Is there any question, any part? Do I have any question?
So were we just working with this example?
Mm-hmm.
Okay.
All I need to do is just really what we got at the end. The corresponding first order differential equation for this type of problems. And what are the notation for? Okay, so R1 is rate in, R2 is rate out, and then whatever is just concentration at the beginning is C sub 1, right? So notations. Any question? This is just an example. I give you time to read the example. This is very just really traditional example, right? So this type of example, I call it traditional because it was originally from any of differential equation classes or books from 100 years ago, and it's always like this. It has just a tank, it does have a salt inside, and it has just something going in, something going out, your rate is giving. So this is a very traditional example, but later on when we finish this one, I have really brand new I will say just differential equation that we can solve by this information. We can just model by ourselves or just formulate by ourselves and then solve that one. There are thousands things going on right now that we can formulate by first order differential equation, and we can solve it. Even just the coronavirus population. That's just the first order differential equation. Okay, I'm giving you the time. Please read the problem. For my first two examples, I have actually listed my information. I mean, you somehow given the equation, but the third one has blank, really means you have to call everything by yourself, and then you have to formulate. It's not formulation because it's the same type of function. You have to call your information from the problem. Okay, ready? Consider this large tank has 1,000 liter. It was originally pure water. And then you're trying to bring the salt, and the rate for flow in is 6 liter per minute. So the rate for flowing is 6 liter per minute. So if I want to use the notation, so that is just really R sub 1, which is 6 liter per minute. And then solution inside the tank kept the well and flowing out with the rate of 6 liter per minute. So means just it doesn't change the volume. It says the same thing because the rate of in and out is the same. And then the concentration for entering. So at the beginning, the concentration was 0.1 kg per liter. Determine whether the concentration of the salt will reach to the value of, so that's the question, whether is this value true or no. So for concentration at the end of this rate in and rate out, stay the same thing or is changing, okay, to that value of 0.05. So the differential equation, so all I need to write the differential equation and solve it, right? So the problem, as we practiced last time, says the change of the salts inside the water is just rate in minus rate out. So when I say rate in minus rate out means concentration in, that's supposed to be highlighted, sorry. Concentration in times rate in, and then concentration out times rate out. So then the information, as you see, just really 0.1 was just the concentration in multiplied by the rate out, which was 6, and then concentration out, I don't know, right? So I don't know what's the concentration out. That's just really what the X is. And then but the rate in is just 6 liter per minute, okay? So then this part is really copy paste of what we have done over here, right? So you have to write a rate divide by volume times the X. So this is rate divided by the volume. The volume is already set to its minimum. Sorry. So this is a rate divided by the volume. So this is rate divided the volume, and that's X of t. So all I did is just plug in my differential equation that I found the other. So let me write my differential equation one more time. So it was dx divided by dt, and then that was R1 C1. That was sorry, subtract. That was X of t, and that was just really what is R sub 2 divide the volume, divide by the volume. Okay, so this is what the formula was on top, and I'm just plugging in there. And these are just really simplification for the same thing that we have on top. And then from now on, so the only thing is it says the initial value is 0. Why? Because it was originally plain water. It's not always, right? So we don't always start from plain water for entire, I mean, just word problems, but here says, right here, says you start with the pure water. So that's why initial value for this one is 0. And that's it. I just need to solve the differential equation as I've done for the previous section. So this is going to be dx divided by dt, and plus 3 divided by 500 of x equals this. That is e, which is, let me call my p of x is 3 over 500, q of x is 0.06, and then e to the integration of p of x dx is called mu, or whatever we call integrating factor. So that's just e to the 3 over 500 times x. And then I multiply this by integration factor, and then on the other side, same integration factor multiplied. So this side was the product of two functions, and that would be always mu times, sorry, I just need to fix this one. That was t. Yeah, that was t. So this is just mu x always times x, because the function is not y, here is x. And then that's just mu of t, because the variable is t. So if you want to call this is just a t, I need to make sure I'm just doing everything. Okay, so it seems I have a mistake. So let me fix all of these mistakes. So x is a function of t. So p of the t, and this is a function of t. So this is a function of t. This is a function of t, because your independent variable is t. So that has to be t. That has to be function of t. That has to be function of t. And that changes to the function of t. So then I'm fine. Okay. So mu of t is going to be e to the 3/500 times t, and then you multiply by the x. This is it. So now if I integrate both sides, if I integrate both sides, that would be e to the 3/500 t times x, and that is 0.06 integration of itself, integration of itself divided by constant. So e to the ax dx is e to the ax divided by a, right? So that is divided by 500 divided by 3 plus constant. So x is e to the 3/500, because I divided by, so that's why I made it negative. And that simplification, I don't have the simplification, so then we have to use the calculator to simplify. So this is going to be 2, and then 5 times 2 is 10 with the 2 zeros, and then we have 1 decimal, so it's 100. And this is e to the 3/500 times t plus c. X at 0 equals 0 gives you e to the 0, 100, e to the 0 plus c. So that gives you x equals 100 plus c. So this means c is minus 100. C minus 100. So my last answer has 100 e to the 300 divided by, sorry, 3 divided by 500 minus 100. Okay. This is really the answer, but I need to go back. If you're ready, I need to go back on top because I don't know what was the amount. Can I move on? Let's see, how much time do we have? Oops, we don't have time, right? So we are done. Okay, sorry, we don't have time, but we didn't answer the question, so I have to stop over here because I have a class right after. So what the question is, whether the concentration is getting to this value, so means you have to get the value of this to see whether your concentration, which is going to be x divided by the volume, and which is going to be the whole solution divided by 1000, is going to be this value. Okay, so we can just really see the calculation whether it gives you this one or no. I don't know what's the answer is, yes or no, but that's just really getting the whether the concentration is going to be that one. Okay, so we have to plug in. Sorry, I have to stop right now, and then we have 2 more examples. We can try it after the break, and that would be a really good review to remind you what we have done. So this is for today, and again I just continue after the break. Everything is ready for you to, let me first stop recording.